going to have maps going this way and this way. Now let me show you what the maps are. You're going to have two maps going like this. You have if you have a line and you forget one of the edges, one of the points of the line is 2 points, then you forget to a point. Okay, so take this line, forget this point, then you're going to have this. Question, which one of the points does it line up to? Okay, you have a triangle. If you forget one of the points of the triangle, you're just going to get one of the lines. So when you forget one of the points, which one of them which lines do you get? Okay, now the degeneracies go the other way, and it's kind of like the identity morphism. It's not very important. The point is as follows: you have this. This is the structure of the set. It's a bunch of sets with a bunch of maps showing how to glue things together. Okay, so if this triangle consists of this line and this line and this line, so then if you forget this point, that's just going to give you this line. It's showing you how to glue things together. It's a very nice, and it's purely combinatorial. Okay. Where they satisfy certain properties, and we're not going to talk about that because he's making me go fast. The empirical model consists of, okay, so now formal definitions. What are we talking about? A simplicial set M of measurements. Okay, you're going to have a set of measurements. It's going to be a simplicial set. Now I got to tell you what each one of the things are. Mn consists of the set of n plus 1 compatible measurements. In other words, if you have Ann, Bob, Carol, Donna, 4 different people, they're all doing, each one of them is doing a measurement. Are they compatible? Yes or no. If they're all 4 compatible, then you have a triangle to describe it. Okay? Okay. The DI, forget the ith measurements. Let's say you have 4 people doing an experiment, and you forget one of them. Then you have 3 people doing an experiment. Okay, you have 3 measurements. So that's explaining how that works. Okay. The simplicial set O of possible outcomes to measurements, O of n is the set of n plus 1 compatible outcomes. The DI, in other words, what's the possible outcomes of the Geiger counter, the spin detector, or the spectra detector, or something like that. Okay? These are the possible outcomes. Okay? Map, then you have a map of simplicial sets. What does it mean to be? It commutes with the phase and degeneracy maps. So you have from the set of outcomes to the set of measurements. Okay? Just like before. And En takes the possible outcomes to its measurements. You'll see a picture in 1 minute. It'll explain everything. Okay? We require that it is weakly surjective. Let me show you what weakly surjective is. We don't just want a map from O to M. We want it to be somewhat surjective. In other words, you have a bunch of outcomes, you have a measurement. You want to make sure that every single measurement gets an outcome. Your Geiger counter is worthless unless you can have some type of outcome. So you need to have this somewhat surjective, and I'll tell you what I mean by that. Okay, what I mean is as follows. Here's your outcomes, here's your space of outcomes, here's your space of measurements, you have a map onto it. Well, you can forget those faces and degeneracies. What happens when you forget the faces and degeneracies? You have a sequence of sets and you forget how they're hooked up, connected, how they're connected. So then you get into something like the whole purpose of topology is to talk about smoothness, and this leaves the space of smoothness. We need this. Okay? You can also forget the space of measurements, and you have a map forgetting that. Okay? It's a forgetful functor. Well, I want this forgetful functor to have a right inverse. Okay? Now, what that means is I want the measurements, for every measurement, to have some type of outcome. Okay? Now, if I was to make this like this, that this should have an outcome, that would mean it's surjective. But that's too strong of a requirement. Okay? In some sense, the non-locality comes out from this part, namely that it's not continuous. The retracts are not continuous. Okay? And we want that this map followed by this map is equal to the identity. Okay, let's look at a real example. That was way. Okay, so here's a real example. I have Ann, Bob, and Carol. I have Ann and Bob. I have Ann, Bob, and Darian. I have Bob, Carol, and Eugene, et cetera, et cetera. These are the possible compatible measurements I have. Now, one thing I can do is I can take Ann, Bob, and Carol and forget Carol. I get Ann and Bob. I can have Ann, Bob, and Carol and forget Ann. Carol. That makes sense. Okay, now let's go up. I have Ann, Bob, and Carol. What are the possible outcomes? Ann can measure red, Bob can measure red, Carol can measure green. Ann can measure red, Bob can measure red, Carol can measure red. Ann can measure green, Bob can measure green, Carol can measure green. These are possible outcomes. And a map like this to this will pick out one of these outcomes. Okay. Now, if we want that these R's should preserve the faces and degeneracies, then we're going to have something like this. Let's start here. I have Ann, Bob, and Carol, and they measure red, red, and green. Then if I forget Carol, I just have red and red. Well, I can also go the other way, namely, I have Ann, Bob, and Carol doing measurements. I forget Carol, I want it to be the same thing. Okay, red and green, red and red and red. Okay, that's if I want it. However, Heisenberg's uncertainties principle says that that's not true. That doesn't happen. What it says is as follows, is that if you have, at certain times, if you have a measurement and you forget about a measurement, you're going to get a different outcome. Okay? So he says as follows. You're doing X and Y. If you do X and then you can do Y, you're going to get a certain outcome. If you do Y and you do an X, you're going to get a different outcome. Well, that's the difference. Okay, so you want to know, what value do I have in X? Well, it depends. Did you first do Y or did you not do Y? That's contextuality, and that basically says that this doesn't always commute. So that's why I need that restriction. Okay, we're not doing that. Okay, so now what I want to do is talk about different of these properties. So here's a typical nice example. You have Ann, Bob, and Carol, and each one can have one of two possible outcomes. Okay, and you have this type of compatibility. Okay, now for Carol, she's only going to have one possible outcome. He's going to have two possible outcomes, things like that. Okay, good. That's a typical experiment with three things. That's a typical outcome with three things. But I want to talk about properties of these three things. So let's talk about outcome independence. We mentioned outcome independence before. What I said was, the outcome of any one measurement does not depend on any other outcome. In other words, if you get an outcome over here of red, that shouldn't affect in any way getting a green over here. Okay, that's outcome independence. One outcome is independent of the other. Let's talk about it in terms of probability theory. It says as follows. If you have three measurements, A, B, and C, and Ann gets red, okay, that's the same as having three measurements, A, B, and C, Ann getting red, but Bob getting green and Carol getting red. Okay? The fact that Bob got green and Carol got red does not affect the measurement. That's called outcome independence in terms of probability theory. But I don't want it in terms of probability theory. What I want is as follows. You have an outcome like this, and you have a pullback. Okay? I'm sorry, you have a restriction. So what this says is delta 1, that's just a line. Okay? You have a line. The skeleton of delta 1, what's the skeleton of a line? 2 points. So it says as follows. If you have 2 points, and 2 points go into a line, and that goes to some measurement, that's the same thing as, and you have 2 points, two possible outcomes. You go like that, then what's going to happen is you can lift it. The line can be lifted. The line over here that these 2 points go in between can be lifted to here, which basically says if you have two possible outcomes, then it comes from some measurements. Okay. Okay. And here's a typical example of something that's outcome independent. Any possible way of lifting these lines, there's in fact a way of doing it. Okay. Let's talk about parameter independence. That's another property. Okay, we're going to do not all of them. The outcome of any one measurement depends only on that measurement and not on any other measurement. So before we talked about outcome independence, what's the outcome of the thing, and we wanted them independent. Here we're saying, no, I want it to be independent of the measurement. Let's talk about probability. What it says is as follows. Ann doing an experiment, getting an outcome A, okay, is the same as Ann doing an experiment, getting an outcome A, and Bob and Carol also doing an experiment. I don't care if other people do the experiment. That's what it means for experiment to be parameter independent. Okay? let's talk about that in terms of this. It says, and Bob and Carol. If you forget Carol, you get like that, and you get like that. What that really says is that, these R's should respect these forgetful functors, these forgetting things. Okay? So in terms of this, what it says is, yes, we had this to be weakly surjective, but we want it also to come from here. Okay? So basically, something is parameter independent if it comes from here. If it's surjective, if this map is surjective. Nicely. Continuously. Okay? So here's a nice example of something that's parameter independence. And basically what it says is that you can lift this map and it's continuous. There's a continuous way of lifting this map. Okay. In between is something locality. Let's talk about locality. The outcome of any one measurement does not depend on any measurement or any other outcome. That is, it depends only on the measurement. What I'm trying to say is locality is both independent of other outcomes and independent of other measurements. Okay? And basically what it says is, given that A, B, and C are done, the chances of getting A is red, Bob is green, Carol is red, is the chances of getting A is red, Bob is green, Carol is red. Product of polynomial. In other words, it's just factors. In other words, you don't take into account the fact that they're all there. Okay? We're going to go through this a little bit quickly. Okay, this is both continuous and like that. I'm going to go just mention some of the other properties. One of the properties you want of your hidden variables, it should be weakly deterministic. I'll say what weakly deterministic is. For every set of compatible measurements, there is a unique set of outcomes. That's what what determinism is. Determinism says, if I do an experiment, I want an outcome. Okay, I want exactly one outcome, which basically means this map, which is what we had before, it should be unique. Okay? There is a unique right inverse to that. Okay?
Why is it weak?
I have to tell you what strong is. Okay. So basically, look at this map. There is one. Here's the measurement. There's one outcome for each one of them. Notice it's not continuous. Okay, and that's fine. This is the core of Heisenberg's uncertainty principle. You want to know what this is? That's that. You want to know what this is? That's that. No problem. You want to know what this is? Well, it depends. Did you measure it like this, or did you measure it like that? If you measured it like this, then this is the answer. If you measured it like that, that's the answer. So it depends on how you measure things, contextuality. Okay? But that has exactly one. Okay, strong determinism is not for every set of measurements, but for every measurement individual. I want a unique determinism, unique map. There's a unique outcome. There is a unique right inverse to U of E. Okay, basically that says that. You'll see it in the example. This is strong determinism. And it turns out that it's a type of continuous. Okay. Okay, fine. So, sorry. That's all the properties with examples of some of the properties. Okay, it's a little bit quick, but let's do at least one experiment. No-go theorem. Okay, this is GHZ. This was a first example of no-go theorem. And basically, it's a theorem that says as follows. There's an empirical model with 6 measurements. I'll show you the 6 measurements in a minute. That does not have an equivalent hidden variable model satisfying whatever lambda independence is, strong determinism and locality. This is a type of Bell theorem saying, look, you can't have both determinism and locality. Okay? And this is the experiment to keep in mind. You have one source giving out 3 particles. So A, B, and C. A, B, and C. Okay? Each one of these particles, and Bob and Carol, can either measure their x direction or their y direction. Okay? So he can measure 1 or 2. He can measure 1 and 2, he can measure 1 and 2, and one of these lights are going to turn on, red or green, red or green, red or green. Okay, so again, as opposed to EPR where we took one particle and we split it into 2, here we take one particle and split it into 3 and send it into 3 different people, each one can measure their own way. Okay, and we're going to get Bob, red, and green. Okay, this is GHZ, stands for Greenberger, Horn, and Zeilinger. 1990, modified by David Berman. This picture comes from Berman's paper. Okay, now I want to show it to you from my point of view, namely with the shapes. Okay, so basically you have Ann can measure X, Bob can measure X, Ann can measure Y, Bob can measure Y, Carol can measure X, Carol can measure Y. Okay, and they're compatible. Isn't PowerPoint great? Seriously, thank you, Bill Gates. Okay, well let's go what it means to be compatible. Each one, Ann, Bob, and Carol, can measure one of two things, X or Y, one or two. Okay, and basically each one of them is compatible with their other ones. However, Ann's measuring X is not compatible with Ann measuring Y. Bob measuring X is not compatible with Bob measuring Y. Okay, so there's no line in between here. Each one of their machines can either be on one or two. You can't have it any other way. Okay, now this is the space of measurements. The space of outcomes is going to be a little bit more complicated because this is a three-dimensional object. The space of outcomes is going to be a four-dimensional object, which is a pain to draw. So what I'm going to do instead of drawing it is I'm going to think of this as an orange and peel it from the top. Okay, and so I'm going to have that AX is going to peel from the top and push down. So you're going to look from the top and push down. And what we get is as follows. Okay, you have the bottom of this thing. Let's just remember, the bottom was AY. So I'm looking now at the bottom as AY, and you have this, all these things. And now I'm going to have AX. I peeled the top of the orange and opened it up, and I have AX like that, and we build it up like that. Okay, this is the type of thing. Now what each one of them could do, each one of them is going to have red or green. Red or green, red or green, red or green, red or green. Now the state of the system is as follows. Okay, I'm going to go a little bit quickly on this. Okay. Notice every single triangle has X, has A, B, and C. Every triangle here has A, B, and C. Different values for A, B, and C, X, Y, and Z. So A, B, and C, A, B, and C. And so these are the possible outcomes you can have for A, B, and C. A can be red, B can be red, C can be green. Okay? I'm just describing a certain quantum state of this particle that you're splitting into three different parts. Now it turns out this becomes a graph coloring problem. Okay? You're trying to color all the vertices. In other words, you're trying to give what is the exact outcome. Now it turns out if you color this, you might say, what about coloring this? Well, by coloring both C and B and C, you're coloring this line. This thing is going to color this line. This thing is going to color this line. That's going to force this to be colored. So you kind of, the point is, and I can't go through it right now, the point is that every one of these regions are colored, and they cannot be colored. They cannot uniquely be colored. It lacks determinism. Okay. Let me just say, there's another, so that had three different observers, each one doing a possible of two things, so that's 6 different measurements. Hardy, a little bit later, did something with 2 observers, Ann and Bob. Each one can do X or Y, okay, and something like that. Now, just let's go, it's pretty pictures, but let's go through it a little bit quickly. Each one of these has 2 possibilities. And if Ann is measuring X, there's a green and a red, 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 okay? And we have the following, describing the following state. This must be true. This red means it cannot happen. Probability 0. That red means it cannot happen. That red means it cannot happen. And now you do some type of thing and you show, okay, this has to happen, this has to happen, this has to happen. This happens, now you have 2 possibilities for red, but it violates what's called determinism. You want only one possibility. You want this guy to have only one possibility. Okay. I'm sorry, a little bit quick. Okay, now by looking at that, I was able to come up with an even smaller example. You have 3 people, Ann, Bob, and Carol, each one doing their own thing. Okay, so again, GHZ had 6 measurements, Hardy had 4 measurements. I call this Turbo Hardy, which has 3 measurements. Okay, and it's a little bit, so it's the same thing, but instead of a square, you can do a triangle. Okay, this may not be, forget about that. Okay, now let's just talk about Bell's theorem. Bell's theorem was about probability theory. It wasn't about yes-no answers. So I can modify my thing. Instead of talking about a simplicial set with a map like that, I can also talk about weighted simplicial sets, because we want probability theory. So for every possible outcome, there's going to be a real number that tells you what its probability is. Okay? But we want it to be finite support. What does that mean? For all dimensions I, for all measurements in the ith dimension, okay, we want that the sum of the weights should equal to 1. Namely, if I pick out something here, I look at the weights that could sum to that, I want to add up all the weights, I want it to get to 1, which makes sense. Okay, this is Bell's theorem in picture form. Okay, namely, you have Ann, Bob, two people, Ann and Bob, each one can do X, Y, and Z, and they're compatible this way. Okay? And then you put measurements. Now, on top of every line, if you sum up the things, you get 1. Okay? And you can restate Bell's theorems in this terms. Okay. Future directions. Let's forget about that one. Okay. Now you can see how I'm going to get to the relationship between compatibility, which is something about measurements, and the relationship of entanglement, which is something about outcomes. Okay? Namely, it makes sense. You can't have a straight line mapping onto 2 discrete points. Okay? That's simple continuity. So that's something about compatibility of outcomes implies some type of compatibility of measurements too. Okay? But I need more work than that, and I also come into some homotopy questions here. Okay. Understand the relationship between probabilistic and possibilistic empirical models. Okay, so possibilistic, that's what we were dealing with GHZ. Relations are possibilistic, they're yes or no. Okay, relationships are more complicated than probabilistic. Okay, next, the Galois groups. Okay, it's interesting to look at, you have an outcome, measurements like this. It's interesting to look at automorphism groups like this. Namely, you want to see how much you can mix up the possible outcomes. What makes the things like that? How much you can mix, how rigid are your experiments? Can you mix up things? Okay, for example, if this is deterministic, the only automorphism like that is the identity. So the group becomes trivial. But if you have less than determinism, you can have all types of things like that, and you get into really nice cohomology theories and like that. Okay, for all the different properties. Give E's properties derive shape of E from M and vice versa. Okay, physical or Langevin property. In other words, look at the symmetries of the possible outcomes and get out the measurements. Okay, so that's like group theory, which is exactly what it is. Okay, these other two, no-go theorem, Koch and Specker. The shape of Koch and Specker, I think, is a Klein battle, but I'm not sure about it. And Conway coaching, which is a complicated shape. Okay, so this is a bibliography. The original paper by me and Brandenburger, Sampson and Bramsky has a nice paper. It's on the archive. They already have a paper, and I think it's on Brandenburger's website. It's called The Unified Chief Theoretic Account of Locality, and my paper is in text form. Well, it's written down, but not written up. Okay, anyway, so that's that.
Noson began to answer questions in private. Thank you for a beautiful talk.
Thank you.
Thank you.